So I'm Deborah Denton with US EPA Region 9, and I work in the Water Quality Standards Monitoring and TMDL section. And I spent, step on gum, never get rid of gum. I actually worked for the Water Board back in '89 and started working in basin planning, and whole effluent toxicity testing is something that I work on. I think I'm going to pause the questions until the end, and I'm around all week, and I'd love to dive deeper than what we're getting into the surface in this fast 40 minutes I'm going to go, because I want to save some time for you guys to work on the homework, and then we're going to go through the answers as a group, if that's okay. So anyhow, we're going to be I'm talking about developing the chemical-specific number. You know there's the three-legged prong for water quality protection. There's the whole effluent, no toxic and toxic amounts. I think we're going to talk about that narrative at some point, maybe in the open discussion. That's the provisions that the state board's working on, but which looks at the interaction of all the chemicals. Then we have the chem-specific, and this presentation is talking about how you derive those individual numerical values for both the acute and the chronic, and for freshwater and for saltwater if we have data. So these are the technical numbers that EPA develops. They're called 304A criteria. And I always like reading from the forward in any of these 304A documents. It says this directs the administrator of the EPA to publish criteria that accurately reflects the latest science and knowledge. So I picked up the cadmium. It's 721 pages long. So, whoops, I went the wrong way already. So the traditional disclaimer, like I said, that's on all our propaganda. Okay, so aquatic life protection is, what is that highest concentration that's allowable, that where we won't have in an acute and in a chronic effect to aquatic life, invertebrates, fish, and that sort of thing. So these are the numerical numbers that we're going to be showing. So this is the part of the act where we're trying to retain the fishable propagation of fish, etc. Okay, this is an example just showing, you can Google EPA aquatic life criteria and you'll get a nice table. It tells you the priority pollutant is an older term from the 307 criteria that said EPA has to establish numbers for all those priority pollutants, and it's 126. Well, right there, what's the limitation of that list? It's 126, so that's why whole effluent toxicity is important. But we're also developing chemicals beyond the priority pollutant. So here you'll see in the table the CAS number, the chemical number that's unique to that individual pollutant, the freshwater. This is the acute value, this is the chronic value, and then saltwater. Okay, so this is the verbiage from actually the, has anybody read the 1985 guidelines for developing these? Okay, they're great. It's the and maybe it's because I'm a toxicologist nerd and biologist. And so the guidelines were developed in 1985, and they go through all the details that I'm covering in a quick 40 minutes. So anyhow, if you want a copy of that, I highly encourage you to look at it. If you're if you're in Rebecca's unit, you definitely know it, and you've got it highlighted. Okay. Good. I find that you have to read something once, twice, 3 times. I do want to go back. I think there was oh no, am I going the right way? Am I going too fast with my finger? Yeah. Okay, so like I said, we've developed numbers beyond the 126. We did it for the new science, the selenium, that came out in 2016. If you don't want to read the large document, EPA puts out these really nice 2-page fact sheets, and that kind of gives you the skinny on it. And so I think that's really helpful. So for selenium, it was actually one value, a criterion, which is a singular, but it has 4 components of that criteria. And so anyhow, new science, an example is cadmium. It was first done in 2001. And as you can imagine, there's more toxicity test data, which is the underlying basis for what goes into deriving that number. So then EPA will hear from the states and you guys saying, hey, it's a priority for us to develop a new number or reevaluate for an existing document, and we did that for cadmium. So we look to you for input. We in California have been saying we need to generate more pesticide criteria, and my very last slide will cover that. Okay, so we're gonna go through step by step. We're looking at the underlying toxicity test data that goes into that source, and then we're gonna be looking at the effects for both acute and chronic. We're gonna be calculating a final acute value. We're gonna be looking at whether we need to consider water characteristics for metals. We know we need to look at hardness for ammonia, pH, and temperature. And so we're developing a 2-prong, the acute criterion called the CMC and the chronic, the criterion continuous concentration. Okay, so we need to look for our effects data. So for the acute, I'm gonna go through this for acute a little slower, and then we're gonna go fast for chronic because it's the same things, more or less. Okay, so where do we get our toxicity test data? We get it from our lovely EcoTox comprehensive database. It's called like the gatekeeper in a way. That's where you would want to go. I encourage you. I printed out the 2-page summary of what that EcoTox database tells you. You can query for an individual chemical. You can query for aquatic. You could query for terrestrial. And EPA frequently updates that based on where they're getting data from the published literature. Environmental Toxicology and Chemistry is a really good journal for a lot of sources of this data. And so that's where we would have the chemical concentration for a range of test species. So I want to say that, when we go through the calculation, it's going to kind of be, a fast calculation. This here, in my opinion, is one of the biggest pieces where you want to spend a lot of time on your problem formulation and your data sources, because you do not want to be standing before your regional board or your regulatory body and have somebody come and say, we found a reporting error, or we question the value that you're using. So quality data to make quality decisions. So EPA spends a lot of time, and if you pick up those documents, that's why they're so big. What data they used? What data did they not use? Was it measured concentration? Was it nominal? What was the control? You have to have an acceptable control. If you don't have an acceptable control and you're comparing that to a chemical, you don't know if your organisms are already predisposed, stressed. So what was the pH, the temperature, those water quality parameters, are they acceptable within the tolerable range for that test species? Because what you really want to be doing is generating the statistical endpoint based on the biology at the end of that test. How many were alive, how many were dead, how many grew and reproduced, and that sort of thing. So this is a huge piece of that whole process. Okay, in those 85 guidelines, EPA specifies a minimum data set requirements called minimum data requirements, MDRs. So this is the minimum 8 families that are required for freshwater, cold water fish, salmonid, a second fish like a bluegill, channel fish. There's a lot of sunfish. There's a lot of different fish, chordata, Third family, planktonic crustacean. This is our classic bread and butter test species that you'll see for whole effluent toxicity testing and for criteria. You pick up any criteria and look thumb through the tables, you'll find toxicity data for Ceredaphnia dubia, Daphnia magna. Okay, whoops. I keep trying to, okay, then bentet crustacean. This is your amphipods, Hyalella azteca. You probably have heard of Hyalella azteca. Terry mentioned yesterday the mayfly, stonefly, midges, mollusks, and another insect in another family. So this is your minimum 8. We mirror that somewhat in our saltwater, minimum 8. This is what the list looks like there. Okay, data requirements. So like I said, for the chronic, for the acute data, it is all lethality and if they're not moving, in immobilization. So for chronic, it gets a little bit more complicated because with the Ceredaphnia dubia, you're starting with a neonate, that's a young, and then 3, 4, 5 days later, she's producing young. By the end of the test, she's produced so many broods of young. So you're going from early to adult to producing young. That is our one of our shortest chronic tests. So for the fish, depending on its life cycle, you could have a fish go from, you want to start with an embryo and go all the way to when it's maturing and it's hatched and produced its young. So you can imagine for some that their life cycle is long. So in those cases where we have long-lived fish, we'll go with a partial life cycle. And then we'll also go with a early sensitive life stage. But you have to know what that early sensitive life stage is. And this is where you have to, the toxicologists have to really scrutinize that data to know. And so you'll see that discussion when you pick up these documents. Okay, so for acute toxicity, we're typically for fish, it's 96 hours, and specifying what age you're starting with, depending on the test species, and at the end you're looking at survivability. You're also, so you might see a term EC, effect concentration, where you had 50% of your exposed in that experiment that are either dead or not able to move. Some of my work in the laboratory was with a neurotoxin, a pyrethroid. And so I thought that the larvae fish were dead, and or alive, and you'd take your probe, and they'd all of a sudden move like sideways and that sort of thing. So basically, they weren't counted as dead, but they're effectively dead. You can't avoid predators, you can't capture food. So especially when you're looking at neurotoxins, this is important. So for the water flea, the Daphnia magna, and those, it's typically a 48-hour duration, and we're not feeding them during that test. So we're only looking at the exposure from water. So that's what those, so we're looking at all those data. This is what the, so you set up your tests, and you always have a control. And you always have so many minimum number of fish in that control, and then you would have individual replicates. I'm only showing one beaker here, and so that's my test control organisms. I have 10 fish in here, and then I'm going from low to high. So this is just any chemical: 13 microgram per liter, 25, 50, 100, and 200. And as you can see, as we go up in concentration, they're all dead at the highest concentration. So then you would use statistical models And the statistical model would calculate at what concentration do I see an LC50 where 50% are dead of the exposed. And in this case, the LC50 is 50. Okay. All right, so we have all our acute data. Now we're going to talk about how we actually derive the final acute value. And so there's a couple of steps in here. So like I said, with the Ceredaphnia, it's a really commonly used test species. So oftentimes what you'll have is, let's see, Carrie might have an LC50 with Ceredaphnia. Rebecca's going to have one. And so I need to take those combined values and calculate a geometric mean for those same species. So that's what we're doing, and then we have to calculate a genus mean. So we're going to go through that. You'll actually need to do this, so pay attention. So like I said, when I've gathered all my data and I've said, hey, these are all acceptable, I've got 4 tests for Daphnia magna, EC50s ranging from 25, well, actually one's 25, one's 30, 35, and 28. So when you get the spreadsheet calculator, you're going to enter these 4 values, and you're going to calculate a geometric mean. And that geometric mean for this species is 29. The geometric mean is used throughout the guidelines because we've looked at, the researchers have looked at like lots of tests, and we know that it's log normally distributed. So geometric mean is the best over arithmetic mean. Okay. After I've done that for all the multiple tests where I have the same test species, then I'm going to actually calculate for the genus mean. So in this case, I have Daphnia magna. I have a species mean of 29. We calculated that on the previous 2 slides. Daphnia pulex, 38, and Daphnia ambigula of 42. So I'm going to take those 3 values, and I'm going to calculate a geometric mean. And that geometric mean is 36. Okay, now I've done that for all the genus in my database, and now I'm going to rank the data. And so I'm going to rank it from low to high, or in this case, they're showing the highest value, rank 4, down to the lowest. Remember, we would have more test species, more toxicity data, because you have to have a minimum of 8. But what we're showing here is the lowest, most sensitive, the lowest values after you've ranked the data. Because what we're trying to do in developing these numbers is protect for 95% of the population, or we're looking at not population, of the species. And so we're really calculating an hazardous concentration of 0.05.
Could you explain where that 95% comes from?
That is discussed in the EPA 85 guidelines, and so that's what the expert team, said. Do we want 90? Do we want 99? And really, it's just the best professional judgment at that time.
And that's for just like this general population, because would that number ever be different for endangered species? But normally we're not really doing toxicity tests on endangered species.
No, correct. Okay, so for threatened endangered species, there's like, if you pick up the cadmium, there are some of the threatened endangered species that were tested. So that data is included in the cadmium criteria. And the thought process is that, in fact, there's a lot of work on this by ORD, Office of Research and Development, out of Gulf Breeze, Dr. Sandy Romano, and it started with some other people, where they wanted to look at that's why the cold water fish is really important to be in there. The salmonids are typically, you don't want to remove, I don't think you should remove them from the database if they're not there, because they're there representing something that you have not tested that could potentially be more sensitive than, depending on how big your database or data set is for that chemical. The more values you have, you're going to have more confidence in that, that protecting the 95. Okay, so we're looking at the lowest four. This is part of the guidelines that is really the crux of how we come up with that hazardous concentration, the 5th percentile. And so basically what you're doing is you're generating these, this is all those individual chronic value, acute values, but the data, the curve would look the same for a chronic, going from low to high. And this is often called a species sensitivity distribution, where you're looking at the concentration on the Y and the rank percentile on the bottom. And it's these 4 values that are going to be driving the derivation of that final acute value. And they're doing this based on a log triangular regression. And again, this is in the 85 guidelines. There's, you know, a lot of smart people that went into developing those 85 guidelines. And I think there's going to be some small little tweaking. When I talk to Office of Science and Technology, you may see some rollout of some tweaking of the 85 guidelines, but no major overhaul is due at any time. So, and why I point that out is this is often a point of question of what other types of statistical models can we use to get this HC5. But right now, the best science is the log triangular.
What is HC again?
Hazard concentration, the 5th percentile, because we're protecting for 95%. So we're trying to estimate what does that concentration need to be. Like this morning when we were calculating the values for the human health, what is that lowest value that we need that where we will not see adverse effects? Okay, so I think I went through that. The log triangular distribution is what's best for the science at this time. And basically, you're taking that ranked value plus n. That's the total number in that data set. So pay attention to n. That'll be part of what you'll need to know in your spreadsheet. How many data points did you use? N plus 1. And so you're looking at that rank. If it was the lowest value, it's ranked number 1, right? 1 over my total n plus 1. And that gives you the probability, cumulative probability for ranking those lowest 4. If you have less than 59 test data points, it's always going to be the lowest 4. So in my conversation this morning with the people that did the cadmium, one thing to keep in mind is because you know that's what's driving the process, those are going to be the data points that are going to be under the microscope by your regulated community. You know, how good was the quality of that data? And oftentimes we're going back and, you know, I forgot, well, later in the presentation, you know, EPA is pulling the data and doing all that work. Then we go out for peer review, and the peer reviewer is going to throw stones. And that's another good document, is look at those response to comments that EPA and how they responded to the commenters. Whoops, again, fast fingers. Where am I? Okay, so real quickly, you know, we calculated the species mean if I had multiple species, and then I did that also for the genus if I had multiple genus, and then I ranked it from least sensitive to most, or from the rank 1 to the highest in the data set, least tolerant to most. Okay, notice the final acute value. You see a problem with that? The problem, you know, is it's based on LC50s. Do we want to set the acute, right, thank you, Julie. And so what we do is we're dividing by, you know, I don't know if you want to call it a safety factor, but we're dividing by 2, and that's your final maximum criterion, the acute value. Okay? So, and then I need to look at water quality characteristics if necessary. Okay, again, this is the species sensitivity distribution. Any criteria document will have this. And so we're looking at the freshwater acute value, and then I divide by 2, and so then this is the CMC. The open squares are the freshwater invertebrates, and the solid are the fish. And so it's kind of, it's showing me a picture, that testing with the invertebrates or more invertebrates is important, and so for whatever chemical this is, it's lead. So understanding the mode of toxic action is important. And, we saw with like diazinon a bimodal distribution that the invertebrates are really sensitive, and you had a big break where the fish, so if you load your data set and not have enough of the appropriate range of structure and function, then, that's going to be a limitation. Okay, so then we're looking at, we just want to stress here that for the metals, that it's really a hardness equation. And so when we had all those toxicity data from individual laboratories, they might be testing at a hardness of 50. Julie might be doing a hardness of 100 for her water body. And so what we do is we normalize it all to a hardness of 100. And in one of your questions, you'll have another tab where you'll need to convert the values to a default, your hardness for your site-specific water. And so we'll show you that. Okay, so now we're going to go through the same steps real quickly for the chronic value. Again, I talked about this where the life cycle, early life cycle, so we're really going to spend a lot of time looking at those endpoints and understanding which ones, you'll see when you pick up a criteria, something may not be usable because they didn't think it was a sensitive life stage. And the statistical endpoints are no observed effect concentration, low X, and EC20s. Okay, again, the same dose concentration response. We call dose for when we're talking about human health, but in this, it's concentration response curves. And so you've got your control all the way up to your highest concentration. And in the past, EPA was looking at the no observed effect concentration of 15. So first you're calculating what concentration compared to the control is where I see a statistical difference. So I have a statistical difference at the 30 and 60. So my low EC is the lowest statistical concentration. In this case, it's 30. By default, my no EC is 15. Well, a problem with that is the spacing of your dilution series, right? And so we're moving towards an EC20, inhibition of 20% effect of what we're looking at, moving away from the hypothesis-based approach for many different reasons, as is the state with their toxicity provisions, side note. Anyhow, this number needs to be changed. This is when we were calculating, using this for the chronic, it's the geometric mean of the NOAC and LOAC. And so that number, it's a typo, so it should be 21.2. So if you could change that chronic value to be 21.2. Okay, moving faster. So next is, like I said, for the chronic, we're looking at the concentration response curve. And so we're looking at, at what concentration do I see a 20% reduction in growth? And so that's called my EC20. And EPA, in some of the older studies, they would have to call the researcher or get the researcher and get the raw data to calculate these EC20s. Because sometimes people, if you pick up, journal articles, they're reporting no X and low X. But this is the way to go. And EPA has a statistical software called Toxicity Relationship Analysis Program. That's free if you want. Anyhow, moving on. So again, we should have the minimum 8 family for our chronic value. And so we do the same thing with the genus species mean. If I have multiple, I'm getting the genus species mean. Whoops. Okay, this little X right here is for, oftentimes you may not have 8 families for the chronic, because remember how extensive those life cycle tests, I mean, sometimes they could be up to a year for the fish. And so the X means I don't have enough minimum 8, but I can still calculate a chronic value based on an acute to chronic ratio. An acute to chronic ratio is just that relationship of, for a Cereodaphne or the same test species, the same water preferably. Actually, it'd be nice if it were in the same laboratory, with the LC50 divided by the chronic value. And so that's called your acute to chronic ratio. We need at least 3 of those values. And with those 3 values, again, what am I doing? Geometric mean. So remember that for going to the homework, because a lot of the places you have to use that geometric mean. So we're getting those for 3, and then we're calculating, taking that acute final value and divided by, the chronic value divided by the ACR. Okay, so this is just another way of looking at what we just went through. And look, checking, what is the word that's important here? Check is QAQC. How good is the data that goes into your number crunching? The number crunching part, as you'll see, is pretty fast. I think that's kind of, in this case, a little, just at the surface. And so really, this is where the beef of your work is going in. Okay, so again, we've come up with, hopefully, both freshwater acute and chronic. Sometimes you'll see that the saltwater, we don't have the data set, so you'll see that's missing there. And then the air expressed as a magnitude, which we just went through, a frequency and a duration. To elaborate a little bit on what Terry talked about yesterday, the duration piece of this is based on the duration of the tests. If I have a acute where I'm looking at 96 hour and 48, would I want to set the duration at 48 and 96 hours? No, because I would not be protecting. Because oftentimes mortality is a delayed effect. And so, and based on the mechanism of action, you might see faster mortality, like ammonia is a fast-acting toxicant. So EPA in the 85 guidelines says, hey, we looked at the acute data, and we find that often if you do a time to mortality, because every day you're measuring are the fish dead or alive, or the insects dead or alive. And so I may be calculating a 96 hour or 48 hour, but I had mortality within 1 hour. So that's how we come up with the duration of 1 hour. Because it's looking at the length of the test to generate that. And then the 4-day is based on what was one of the tests, Cereodaphne, I said was 7-day. So we want to be shorter than some of our tests. So that's how we come up with the 4-hour duration. The frequency is field-based. That's based on, and a really eloquent discussion of this is in your White Bible, the Technical Support for Water Quality-Based Toxics Control, Appendix D. I reread it over the weekend to remind myself. And so the duration is based on if I have a catastrophic event, or if I have concentrations that are at this high level, what is the time that it's going to take for organisms to recover? And that's going to depend on where you are in that stream, order, refugia, and that sort of thing. Insects, shorter life cycle. But then you think about our fish, that, it might take them a lot longer. And so 3 years is our return frequency. These things are the criteria. Now, a whole nother class is how you take those duration, frequency, and magnitude and fold them into permit conditions expressed as 1 day maximum and 30-day averages. And that's more statistics. That's also in this white Bible. Okay, so Terry's going to talk a lot about site-specific criteria, so then you're getting into, again, what's your formulation statement? Why do you think that, you need to do something different for this site or this site? And so pick up those criteria, look at those, because that will help you to think through why do you think you need to do something different. It could be based on either the sensitivities of the species may be different. Maybe you have something that's more sensitive. It's not always going higher. And so, or the site specifics of the bioavailability. So Terry's going to go through this, how we calculate for a water effects ratio. So in the laboratory, in those 85 guidelines, I can't have dissolved organic material greater than 5 milligram per liter. So if I have water characteristics where I know it's much greater than that, there might be something that mitigates or reduces the toxicity based on the particles in that water. And so what would be, do I have enough data to say, what do I want to set that at? And so the WEIR, the water effects ratio, is looking at the effect of that site water in relationship to the standard lab water. Okay? Whoops, I think I went one too fast again. Okay, some other acronyms. Acronym soup. BOMs, biologic ligand model, those are used for copper. Basically, the fish are the most sensitive on the metals. And that's because they're binding with the gill membrane. And so those metals are competing for sites, ligand sites in the membrane. So if you disrupt the osmoregulation of those fish, you can imagine the stress that they're under. So the BOM is mimicking that interface. So it's got, again, we talked about data. So data is going to be important. Do I have enough information on the site chemistry, pH, DOC, temperature, 6 geochemical ions, cadmium, calcium, magnesium, potassium, sodium, sulfate. And so we have to have data. How good is that data that's going in there? And then EPA is working on some stuff with the multiple linear regression method. It's a statistical process for aluminum based on 3 or 4 water chemistry parameters. We've spent 2-3 decades understanding the bioavailability of metals, and that's partly why I have a little issues with pesticides and saying that we can just do bioavailability with pesticides, because it's a lot of work that goes into this. There's a lot of scientists that are working on this. So EPA recommends that for copper. We're in an agreement to develop some more for with 8 other metal associations. I don't have a timeline, but you can go to that document and see what they say. I thought I had one more slide. Okay. I wonder why it's doing that. Anyhow, EPA review, I talked about this. Peer review, peer review, peer review. The state has a really good process also for the peer review. These numbers are not standards. Not until Rebecca's team says, I can either use EPA's 85 guidelines and, include more data or less data and write all that up, go out for peer review. That's one option. Or Rebecca could say, hey, I want to use EPA's 304A criteria. And then when she says it's there in the statewide standard, then that's when it becomes a standard. Okay, last slide is I just want to highlight we have a lot of pesticides as impaired water bodies here in California based on pesticides. So Regional Board 5 had the foresight about the mid-2000s, and they had a contract with UC Davis to develop a methodology I have the links there. They have 2 really good reports for those people that are really into this stuff. One was looking at all the methodology worldwide, and so how to develop guidelines. Actually, the lead author in this is one of my good friends, and once she finished her postdoc, we swooped her up and said, come work for EPA, Patty Tenbrook. And then the Board 5 has developed numbers for a list of pesticides. What I do want to point out is something that I really like. There's a lot of few things I like in there, but the one I want you to keep in mind is they have a table called R&R. I call it R&R, reliability and relevance. So remember when I talked about the quality of the data? It goes through this checklist, and you have to answer all these questions, and you come up with a point system for what was included in that analysis. What was the age? Were they fed? What was the temperature? What was the quality of the control, et cetera? So just want to point that out. All right, now I think we're on to quiz. And, question, Rebecca?
Well, I just wanted to come back to what you were saying about the process that California would go through for incorporating this process into individual new water quality objectives. That's certainly the case. But there are also, I think, correct me if I'm wrong, quite a few of the aquatic life criteria present in the California Toxics Rule that currently do apply to California waters. And if you're not in California, there's the National Toxics Rule that will likely apply to other states. I don't know exactly what their rules are. But so, and I am assuming that this process, this intense process of looking at the effects of metals and other pollutants, other priority pollutants on aquatic life is what was used to get those numbers into place.
Yeah, that's right. And because my presentation was talking about how to derive those technical numbers, and then when the plan was rescinded, we had a state with no standards. And so we had to fill the gap with the National Toxics Rule for certain chemicals where we had those. I don't know what those are. We have a colleague that's our expert on this. And then we developed the California Toxics Rule. And so basically EPA said, we're going to use EPA's numbers. We're going to take those technical numbers. We're now going to call those the criteria for Section 303. Thanks, Rebecca. And the nice thing about that, when John Marshak would always give this talk, is EPA in doing that promulgation doesn't have to consider economics like you do for the Port of Cologne. So you have that harder little lift there where economics analysis. So yeah, those are good technical numbers. A lot goes into that. I mean, when I look at this 921-page cadmium document, and I think any state that wants to go off and do that on their own, I would be pushing headquarters and say OST and say we want more numbers, you know, for a lot. So anyhow, that's that. Any other general questions? And I'm here and I'm happy to talk to people, you know, about this stuff. But how do we calculate a genus mean acute value? We would find all the species. Remember, I had, so keep this in mind when you're looking at your homework. Is there multiple tests results for the same genus and species? If not, then you use that single value. And then you would calculate the genus mean value, because I had 3 different data points there. And so then I would, on your tab for calculating the geometric mean, you would enter those 3 values to calculate the genus mean. Oops. Okay. How many different taxa are necessary for the minimum MDR? Yes, 8. Sounds good. If I had 26, which ones are going to be the most important for the derivation? Perfect. You guys are ready. Okay, so pull up your, I think we're taking off this.